let's now look at some of the threats of fingerprint. And first, I'll introduce you the how the fingerprint systems work typically. Then I'll introduce you how the classical threats are there, and then from there on, we will move towards some synthetic generation of fingerprint. Um, the code for synthetic again, it takes some time. So when you go back today, just let it run so you can generate the synthetic fingerprints, and then we can test it. Okay. All right. So has worked on fingerprints so far? Nobody? Okay, that's good. So then we get introduced to the fingerprint, and then we can continue for the attack, right? First, one of the things fingerprints is that this is epigenetic, which means that the identical identical twins have different fingerprints. But they have similar shapes, but the minutiae will be very different. And again, according to the studies that are documented so far, it is documented that it's formed early in the period of the gestation, so between the pregnancy and then post-pregnancy, right? Don't change. And one other thing about the fingerprint is that the fingerprint is typically encoded in subskin, which means if I get rid of my top skin, the first layer of the skin underneath is still having the same fingerprint, okay? Which means it gives a bit of stability and robustness in terms of regrowth of fingerprints. Sometimes it might happen that you have very deep cuts, and then the deep cuts means that it can get rid of a couple of layers, right? The cut can go very deep, and that might have a bit of a problem with okay, and then there is also a bit of a problem with the scale. When we, if you have looked fingerprints of the babies, see that the fingerprint is very small, right? It's very, very small, and then it scales up as we grow, as we age. So there's a bit of a problem. So this is also a problem that is very understudied. And the problem of the deep scars is also very understudied, mainly because we don't have such data sets for studying. And then there is another problem, which is quite common in the case fingerprints. It depends on what kind of fingerprints you are actually using to capture the fingerprints. So there was a question in the morning about the different sensors. Talk about it in a while. And then in addition to that, very often if you have your fingerprints which are dry, then this also impact your image that you capture. And then many of us who have this manual labor, we also tend to lose the fingerprint. And this is a common problem in the farmer population, especially in India, right? So when you have people doing a lot of hard work in the grounds, then you have the loss of the fingerprint. It regrows, but at the time, when you're capturing, if it is damaged, it has a okay, and then the other classical problem with the fingerprint is that you have this deformation, right? So what do we call about what mean by deformation is that every time I capture a fingerprint, I press my finger onto the surface. So because I press it, depending on the pressure, depending on the amount of contact I'm making, it might be very different. Again. So which would mean that very often you have to deal with partial fingerprints with actual, right? So the police officer was sitting, he will ask you to press it properly, and then maybe he will help you. But when it is actually to verify yourself, you might not be pressure, not exactly the same. And we all tend to do that, right? We all tend to do that. Sometimes we put it a bit of more pressure, sometimes not, right? So this is a bit of a problem. In addition to that, there is also some studies which have been perspiration. People sweat, and because of the sweat, there is fingerprint. You not really lose the fingerprint, but the quality of the fingerprint that you have there will be very right. Okay, so then there are some advances in this case. So each of these problems can be solved with solved in a different way. That I'll talk about it in a while. But Okay, so in the case of the fingerprint, right? Fingerprint is one of these approach that has been in the biometrics for very. So if you look at the literature, you can start seeing the appearance of fingerprints in the late 1800s, and it was used as a mechanism for access as a tool, right? And then in addition to that, in the earlier documents we see, it's also shown that it was a mechanism that it was true that it was your own problem. It's the same case even in India. If you go back to the old documents, you see the property registration document, there you do not see a signature. You typically say thumbprint. Although it was called thumbprint, later it was extended for other kind of fingers. So you have this classical applications, and even today, the government of India, for at least in Karnataka, they use this fingerprint as a registry. It's the same here, right? And the same reason why it's also connected to the others, right? Because you have cross compartment. One system can be connected. Okay, and even today we have this very wide system which is popularly used in European visa control, border control, where there is a large database which is called as the systems and Schengen information system, and they share the fingerprints across different. So since these are large scale, we are talking about not just 10 million to 500 million. With recent production, it's even much bigger. Okay, and other than that, where else can it be used? It can be used for watch list. When we say watch list, if I'm interested in finding out if a certain person is present in that scenario, so then I can just look at the fingerprints, assume that they are available, right? So I can watch a particular person, and then this also means that I can do the blacklist of a person, right? So if I identify a fingerprint, then I can also say that do not do that. And then, as you can imagine, the fingerprint devices are typically very small. They're not very far from the machine. So they capture the fingerprint and you have to process. And since you're doing this one-is-to-many searches, occasionally in the case of visa control, so border control, it might end up with 1:1 million search. And your search has to be extreme. So then comes a different field, which is called as indexing the database and then create it and then fast indexing that database. All right. And then there is this two other case. One case is this forensic applications, and the other case is this typical access. In the case of access control, what you would do is you would try to look at fingerprints in an automated manner, and then you can grab them. But forensic case is slightly common, right? Because you have noise, you have latent representation of the surface that you're touching, and then partial, multiple overlap on each other, and this kind of common challenge. So what happens in the case of forensic application that not just the machine that is making addition, but there is also this forensic examiners who are sitting and trying to match how they try to compare this. So there is a very big research field that is going on there, but unfortunately there is not enough manpower to automate all these processes. Okay, so just to recap to what we discussed yesterday, we saw this typical pipeline of recognition system, right? So any kind of recognition system starts with a capture device, and that is your camera, that is your smartphone, and so on. And you have variability which is coming from the sensor itself, from the subject itself, and from the sensor. So my fingerprint today and tomorrow might be slightly different by the way I touch this. And then sensor itself is aging, right? The camera that we buy today, 5 years time it might be without. So that there is a sensor pipeline. And then once you have that, rest of the pipeline varies, right? You have the feature extraction, right? And depending on the threshold that you determine, you say that it's accepted or there is nothing that changes except the part here where the feature extraction mechanism is very specific to this kind of. All right. So if you go a bit further, let's try to look at what makes fingerprints unique. So now if I give you this image, you can see that there is number of characteristics that it has, right? You can see that there is a specific way the fingerprints are forming. Each shape is very different. And then if you look even very closely, you see that there is a distinct pattern of disconnections here. See that? A small disjoint. And these are also because of the sweat pores. So there has been also studies which talk about how the sweat pores are very unique to this, but not as an independent modality, but as a additional one. So if I have fingerprint details plus the sweat pore details, okay. And then whenever we are talking about this one, we are talking about these ridges. Ridges is nothing but this these ones that you are seeing, the dark ones. And then when you have the ridge, then you also have the valley, right? There is a ridge and a valley. So we look at it as a 3D surface. You can look at see that very subtly goes up and down, up and down. Okay? And then whenever we are capturing the fingerprint, especially in touch-based sensors, we are talking about variations which are introduced to the image quality, the picture variation, as I put before, or the scratches, or the wetness and the dryness. So every single component here will factor and then you have the shape variations. The shape variations can be coming from different part of the finger. For instance, if I'm capturing full finger, or if I'm capturing only the part of the finger, then it has still a fingerprint, but it's still partial. And then you have the other aspect, which is rotation, translation, and scaling. What do we mean by rotation, translation, scaling? We have seen the device is used in other. See that the sensor is quite big, so I can be placing it straight, I can be rotating a bit, and then or it will slightly right? So all these factors will have some. And then because of the pressure, there is also some kind of elastic. Okay, and then there is also this Henry classes in fingerprint. Henry classes in fingerprint actually is that so the Henry class of fingerprint in fingerprint means that all kind of fingerprints that we have, the whatever is been documented so far, can be kind of classified in these classes. So if you look at them, you have this arch, which is visible in most of our fingerprints. And then you also have tented arch, which is slightly different here. You see that it's a typical arch. And then you have a tented arch, which means that there is a small triangular shape that is formed. And then you have the delta, which is the left loop loopings towards the left, and then the delta goes towards the right? See, there is a subtle increase, but this is like a common kind of fingerprint structure that you find in most of them. And also you have opposite to the left loop, you have the right loop, and then you have the hole, and in the hole you can have also twin loops. Now here, if you look at the hole, it's like this water running into a stream, right? You have seen that common phenomenon. And then there is a hole here, and there is a hole here. And in the case of the twin loop, you probably will have almost like see the structure of S, and then there is a delta here, right? So any fingerprint that you see is typically known to exhibit these documented results show that it's 6.6% of that, 33% of this, 27% of that, and then everything together is up, right? Okay, good. So now this is the classification that was done very early in the literature. And now if you go to the capture mechanism, there are a number of ways you can capture. So one of the traditional capture, the very, very old days was the papering. And then what you take is that you remember this kind of carbon, well, a lot of things. Then you put it on that and press on the stamp file, right? Exactly, stamp file. So this is typically the scenario here, and this is how the were collected, not performed. And then you have the second one, which is rolled, which means you want to capture the whole. press it, and then you go. And the common application of those is forensic. Let's say there is a crime that has happened, and then you want to establish whose fingerprints belongs, then invite all the suspects, and then the suspects are suspects that try to match them. And today we have gone far, far away from that. What we are talking about is the sensors that are connected. So most of you might be having the laptop which is fingerprint enabled. Most of you have the smartphones which is fingerprint enabled, right? So there we are not capturing this whole big content because the sensor is not so big, but even the minute small area that you have with that sufficient image. Okay, and then there is also this sensor called as slab sensors. This is typically this one, right? So I can capture multiple and not just the fingertips, but I can also capture other information. So you can extend information. And then you have the commercial sensors, which are even more smaller. Then this can be used for um, and then you have most modern day systems have gone away from this kind of touch-based movement, especially the trend has changed after the year. So when COVID hit, when people were not happy to touch any of the sensors like that. So the field has moved towards smartphone-based fingerprint capture, and here two more. One could be your own the sensor is integrated on the smartphone. Some of you might be having this Android or Google smartphones which has this fingerprint on the backside of the phone. Or you could even go away from that and say that okay, I do not want to touch the fingerprint, but you can just capture it using your phone. And this is what is typically called as the finger photo. Okay. And of course, the quality of that was not as good as classical fingerprints with so much of detail. But now there have been a lot of methods which can actually match the fingerprints or compare the traditional fingerprints with. In addition to that, also this the details about this what kind of sensors. So one of the sensor is this optical. So by optical, what we mean is that there is a camera and then there is a light source, and then you're putting the image, what do you say, flashing the light surface, and then you're capturing, right? So this typical classical physics. So you have the light source from one side, and then you have the imaging source here. So every time the fingerprint hits, the light hits the fingerprint, then you get a reflection, and then you capture. Okay? So this is classical. And then because there is a certain amount of electricity in our body, you could also use that for captive, right? So the surface that you're getting, surface that touches here, it can release some electricity information, or electricity, let's say, and then you can have a circuit which captures this content. And this is what is called as the capacitor. And now this is also kind of understandable, right? So whenever I'm pressing the fingerprint, so this part touches and this part doesn't touch, which means the information from here is recorded as a black part, and the information from here is recorded as white part. Okay, so this is a common thing. And now, in the recent years, there have been also studies which have gone towards optical multispectral, which means here you can see that it's only one light source. Okay. So what happens if I change one light source to multiple? So then I have multiple. So then all this multiple information will capture the information which is not captured by one other light. So then I get complementary information, different spectrum, and then I can have a much better representation. Okay, even going further from what has happened in the last years is that this optical touchless. So now you do not really have to do the interaction system. All you can do is that you can go to the system and then you swipe. Not even touch it, right? So the swipe speed was extremely slow in the first part, but now the modern day sensors, they do not have it. So you can just walk through the corridor and then you swipe it. Okay? So there has been massive progress in terms of capture mechanism. But the olden systems, or most of the systems that we have, they are still based on the databases that we have. They are still based on capacity of the system. And hopefully the field is changing towards more modern systems. Okay, and then here are some sample images which are being captured from fingerprints in terms of scanning. And on the top layer, you see that in the top row, you see the image of good quality. Although visually you might say that, okay, this is really not good quality here, but you see that here it's quite good quality, but there is still some of distortions. And if you have a extremely low quality, then what you're going to get is that you're going to get an image something like this from the same sensor. And now here you don't see any, right? Then comes the idea of the pattern that we introduced yesterday, where we have to do an two options here. Either you can say, well, I'm not happy with the quality here, you recapture this, or you can say that, okay, I start with whatever the image that I'm getting, I try to enhance it. Okay, okay now it can be even more extreme in some cases. For instance, if you look at this one, this is completely noise, right? So it's not usable at all. And again, the same thing here. So there is works which are being done for establishing the quality itself. NFIQ is one of the examples, NFIQ1 and NFIQ2. For those of you who are going to work on fingerprints, I strongly recommend that you take a look at that. Then you can use it for establishing quality. Okay, now if we just take another example here, the previous case, if I'm capturing two fingerprints of the same person, let's assume this fingerprint, right? If I'm capturing in one instance, I see that there is a lot of gap here. And if I ask the person to move the fingerprint this side, maybe I'll end up with getting some space here, which means I might also get some additional. So this means every time I'm trying to compare two images, the information might not be exactly the same. There is a bit of a change in the information, and this is a common problem in any of the environmental systems, except for some models where we have extremely constant. So if I'm going to create let's say a simple pipe, then I ask people to place in the pipe, then I can consider. In any other cases, you're going to have this problem with the registration. So what we need to do is that the process of this normalization, we also need to as this. Now this registration is it's a right? It's very simple. So what you need to do is you need to find some reference point, and then you try to align every other point to the thing. Yeah? It has some standard set of fixed x and y, and then the next image that you're getting, try to find the x and y of that, and try to map it first x. Okay? So it's a classical idea of normal. And when we are doing this, there are also some other small steps that we do, but very important steps. The first thing is second. So I'm interested in registering the background, right? I don't care about if there is a black pixel in the background, but all I care is about the fingerprint information, the whole area of my fingerprint. And now here, um, one of the other common observations that you would make, or when you're trying to use the fingerprint, that your image might be rejected. And the rejection might come from the fact that it's not banded, right? It's the dots per inch. So those people who have some idea about this printing, you know that it's how many dots you're printing per inch, right? So for your fingerprint to be usable, to be compatible with most of softwares, it should be around 5. So modern day it's a bit more, but at least it should be. And then you have the registration, which I told you. See, the registration can include multiple components. It can be just rotation, or it can be rotation plus that, which is the same thing that we do in face recognition. Well, so we try to align, right? We try to make the pose as much as sorry, yeah, head angle as much as possible, and then we try to make it. Right? So it's exactly the same thing. And then comes the next part, which is enhanced reach and value graph. Because we saw that there is a lot of discontinuity between the edges. there might be some noise that might be present, so we might want to remove them. So we might want to remove scratches that are coming just from the sensor. After all this thing is done, then we say that, okay, it has been formed. So which is typically what we call as feature, what to say, image enhancement phase. Okay, so what exactly happens in the case of a normalization? So now you see that if I have an image here, and this image is upright, very well aligned, and then you have the second image which is captured slightly different setting, then I see that the image is not exactly in the straight angle. So what I need to do is I need to align. Now the alignment can vary depending on how you determine the point. For instance, it can be absolute. I single image should have the X point exactly at here, the highest X point and Y point, and then I can try to put this one, align this according to that X point, right? But then there is a, because this information, what you're getting here, might not be exactly the same information that you're getting here. What happens if I'm getting only this part of the image? So then my absolute alignment will fail. And then you have the second part, which is relative. It's slightly better because in that case, I can say, I determine this point, I determine this point, and then I try to align these 2 points with respect to these 2 points. Make sense? So then it's this absolute and the relative one. But again, for doing both absolute and relative, you could also use of this core and delta, uh, where here core of a particular point, and then I can say, okay, what is the maximum amount of curvature that I have, and then what is the direction? So here I can clearly see that the core is going toward this direction, right? Upward direction. Then if I know that, and I see that, okay, this is also not in that direction, then what I need to do is I simply rotate this image, or I rotate this image to the right. Okay, so every single image that you try to establish those points, and then you try to recalibrate. Okay, and then he wants to work on these kind of images because you see that a lot of information is missing, and the same here, parts of the scan are completely missing. Now, if it was a small, minute area, I could think that maybe it is sweat code, but now there is a large discontinuity of this information. So what I need to do is that I need to improve it by pre-processing. How do I improve it? So first I can start looking at these values, looking at these reaches and see, okay, this is a line that continues all the way. That means that this information that is missing is actually the missing information. So I can fill it. So when I fill that information, see that point here, 1.8 becomes more line, right? So when I do this, uh, the goal is not only to make it look much better, but the goal is to approximate this kind of ridges and bifurcation and so on, which I'll talk about it in a while. The natural pores will also get, right? So this is why we told natural pores, wet pores are not unimodal, so you cannot use it as a single modality. You should always use it with other. So here the goal is to extract this. I don't know if you're able to see that, but can you see this small white edge here? And then you see this the merging of these two lines and the bifurcation of these two lines. So those are the information that we want to extract from case first, right? So the first goal here is to improve it and then go back to the information to extract more. So to extract the core, delta, and minutia, so we make this up. Okay, and then just to connect to the today, if you remember, we did this Sobel filtering. I don't know, yeah. So which is what exactly we can do here, right? I can do directional filtering in X and Y. Every time I do a directional filtering in this case, X and Y, I can see that the information gets more and more clear. Then I can put all the information. Yeah? So all those things go back to the approaches where I can look at, try to see, okay, the edges are missing. So I want to reconstruct the edges. So I do the filtering and then try to. And then comes the second part. Now, if you look at this one, all this information is useless information, right? So I can simply set them to 0. So by doing that to zeros, I only deal with the information that I can trust. Okay? And now this was done in a very classical sense in previous cases, in the previous generation. And in the new generation, you can learn a system, you can learn a deep learning model, which can go from that image to this image automatically. Right? So this is typically the enhancement end-to-end pipeline that you have with deep learning. Okay, and then comes the next part. The next part is what kind of features are we talking in case of Fingerprint. So in the case of face, we had two options. Yesterday we saw that we do it with classical machine learning by extracting features, extracting the histogram, then try to match it to distance comparison. And then today morning we saw that we could do it in a deep learning. So we learn a network, and once we have learned the network, we give the image. It gives us a feature of pi 12 dimension or 120. In the case of fingerprint, the extraction, the features that we extract are slightly in the classical sense. The classical sense that would be these features, right? So we are interested in extracting these curved lines, which are ridges and valleys. And then we have the global shape, which is typically called as level 1 features. And level 1 features would mean that what is the direction of the field, how many ridges are appearing in a particular area, and then you have the curvature. So what do we mean by global features? Now, if I ask you to look at this image and tell me how many ridges are coming in this line, you can easily say that it's 1, 2, 3, 4, 5, right? So the frequency is 5 per area that is considered. And that's a easy thing, right? It's something that we can easily locate. That's why it's called as level 1, something that we can easily extract from the image itself. And then comes the second one, which is local details, where we call it as minutia. The minutia consists of location, orientation, and the type of the bifurcation, and the type, which is either bifurcation or endpoint. For instance, if you just take, let's say, this area, right? So this part, now you can see that it has all these three properties. It has a location, it has an orientation, what kind of angle it is looking at, and is it a bifurcation or is it an endpoint? Now, this is an endpoint, right? So it is ending at this particular. And then you could also think in the bifurcation area. Let me find a bifurcation here. No, not that one. Here. So this is a bifurcation, right? This one that is going here, it's getting bifurcated into two parts. So this is something that you would want. You cannot obviously spot it. So you do it at level 2, or you need a detailed look. And then it's the third one, which is level 3, which is the sweat pose that we are talking about. If you get a very high quality images, you will start seeing this small, minute sweat pose here. And sometimes it might be also very confusing because your scanner might not be able to capture that, but it might appear like a sweat port, but it might be missing information. Okay, so these are the information we are extracting. And when we are extracting these information, you would want to compare them using similar kind of. So the traditional approach is to do the minutia versus minutia. So you look at each minutia, then try to match how many of them are matching with the other. And then you could also do the matching based on bifurcation and the endpoints of the reply. So if I'm giving you these two images, you can see that, okay, there's a bifurcation here, let's say a bifurcation here, but there is no bifurcation here, right? So you match point to. And this is typically the way that humans match, right? So if I give you two images and ask you to look at this, you would be looking at each pair and then trying to see if the pair has similar colors. But the problem is that it's very complex, right? It's also very slow in terms of process. If I ask you to look at 100 images, you probably will take 10 days to do all them. And then you have to do one versus all other one, right? So it becomes a slightly complicated problem. So what people have done is that they have standardized this comparison mechanism. They have said what information we use for comparing. And this is what is called as, this is what has been documented in the ISO standardized format. And then comes the second one, shape comparison, which is image-based approach and the direction of ridges. And then these are typically computer driven, and then the process is quite fast compared to the first. Instead of minutia comparison, the second case is much easier, much faster, and then it's also good for low quality comparative, right? Now, as soon as I start talking about this shape comparison, this is image based, right? As soon as it is image based, can I not now think about using a deep learning model? So the most modern systems now are not just basing on the minutia, but they're basing on this image based approaches, because now we are dealing with the shape and the structure of things. Okay? So there have been many recent works which actually talk about which have very good performance for purely deep learning based systems. Okay, and then once you come to this point, what are we talking about? We are also talking about the features that we are comparing. As I told, whenever we are talking about this minutia, so we are talking about two different aspects, oh, sorry, three different aspects, which is the location, the orientation, the type, and the location, orientation, and the type. So which is, the location is represented by x comma y. In every image, we have a spatial position. And then the orientation is nothing but the angle. Is it at 90 degrees, is it at 30 degree, and so on. And then we have this T, which is nothing but what kind of minutia is it? Is it a bifurcating minutia, or is it the endpoint of a big line? Right? And now put all of these together, and this information can be used for, first we register them based on the minutia, and then once we have the minutia registered, then we count the total number of minutia in the same range, same location, and then we determine the score of the comparison. Now, the score of the comparison is nothing but you consider a particular radius, and then you try to find how many of them are actually matching. Right? Maybe it is 10 out of, right? But we still have 20 matches of this, 10 matches out of this 20 points. But although it looks very easy, what you should also remember is that the registration is slightly difficult when we have the elastic, because if the image is like this, and let's assume the image is a bit stretched, that means the information that you're getting will not be exact. So the classical comparison of minutia might be very tricky. And then there is also the other problem, right? Sometimes you might have missing minutia. Sometimes you might have spurious minutia. The spurious minutia might come just because your fingerprint is trying to capture after a previous capture, and there might be another line that is coming out here, and this line might be causing a spurious minutia. Okay, so these are some common problems, but then the comparison remains very standard. So what do we do? So the elastic deformation, something like this, right? So you have this images which are captured in three different captures. So you see that there is a red line, there is a blue line, there is a black line. Okay? So just try to focus a bit on this figure, and then you can see that this area, the information that was here has now moved to some other information, right? And then because of the way the fingerprints are captured, okay, this is an enhanced version of the fingerprint after processing. And now after processing, you see that none of the lines are actually matched. There is some match, okay, here and here and here, but most of the other places it's displaced, displaced everywhere. So if I tell you that are these two fingerprints the same, you would probably say no, right? So this is the same problem that will happen with the automated system. And then you see one way to deal with this is that you can say, yeah, I don't want 100% match. I can have 30% match. I can live with. But if you decrease the threshold of matching, then you are also going to accept a lot of people who are not actually the right person, right? The securities. So if you're trying to improve the convenience, your security will go, right? So that is a problem. And then if you're doing that again, okay, you can see that FMR and FNMR, you had the lecture this morning today, where you saw that FNMR and FMR are connected. So if you compromise on one, you'll compromise on the other. Okay, so what can you do? theoretically, you can assume a model. Okay, this is how the image has been modified, and then you can try to remodel. Right? So if I know whenever I'm doing, let's say, a repair of the car, I remove one after the other. I know exact order what I will screws and nuts and the bolts. Then I can put them back in the same order. But that comes with the knowledge that I have this complete thing documented. If I just throw you a bunch of nuts and bolts and whatever the screws, they'll not be able to connect, right? Because I do not have that inverse knowledge. So for this case, we need to have the inverse knowledge to go back to that one. And then very often it is a problem that we do not have this unconformed references. So every single time I'm capturing, what is the right one which is not deformed? And it can be deformed, right? Because of the way I interact with the system. And then is a alternative solution. What you can do is you can do an elastic comparison. Say that, okay, the estimated somehow how much there has been displacement. So how much has the finger moved from A to B, and then I try to compensate for the comparison. Okay. Slightly more elegant because in the first case it's very almost impossible, but the second one is feasible at least. Okay, and then if you think the same, what can you do? In the solutions, you can think that now we have established that true distortion inversion is not possible. When I say not possible, it's theoretically not possible, maybe practically to some extent. What can we do? We can also look at, to do that, what is the other problem, right? So we also need to have the corresponding points. So in this case, if I do not overlap the images on each other, I do not have any corresponding points. So that forms the first problem. So what I can do is that I can also try to compensate at the comparison level, as I said in the previous case, where it might be tricky. So then comes the second solution, right? The solution can be local comparison versus global comparison. What I can do is I can look at the whole image and then try to say, okay, there are at least like 30% matches in this image. And then I can divide the image into number of blocks, small blocks, and I can say, okay, in this part of the image, I see that it's, I don't know, 20% match. But in this part of the image, I see it's 30% match. Maybe in this part of the image, it's much more. So then I have multiple decisions from each block, which I can put together. Right? So if 5 of the blocks say that, okay, this is matching like 90%, then I'm very sure that it's 90% same match. Right? If 5 of the out of the 5 blocks, it's 4 of them are saying it's 10% match, and only one block says that it's 90% match, then we know that it's likely it's not the same. Okay? So this is these are other problems, and then the alternative is also to look at the neighborhoods. So when I say neighborhood, what I can say is that look, I have a minutia point here, this one M0, and then right next to this neighborhood, I have a couple of other minutia. So I have M1, M2, M3, and in the second image, if I'm getting this one, and if I'm not getting these three, then I know that they are not matching. Make sense? So it is like you are putting the additional information into the system, trying to say, okay, if I'm getting one minutia, then it should also be coming with a set of minutia, right? If it is not coming with set of minutia, then it's likely that there is something that's spurious. And this approach is slightly better because in this because it can tolerate the false and the missed minutia when I'm capturing it. And the second part is that it can also be good for comparing substructures. So as soon as I'm talking about this one, I could also say that, okay, this minutia has something happened.